All right, guys, we are going to get started. I guess, does anybody have an answer to the first question? No? Channels? So channels, I guess, so a form of communication, a way to express communication. Anything else? Yeah?
Some way to do asynchronous stuff easily.
Yeah, so kind of like threads. You had one? File handling. So basically, we're starting off with this question because this is the Go tutorial for 416, and Go happens to be a language built for building systems and distributed systems. My name is Amanda Carbonari. I am a graduate student under Ivan, and my focus is in distributed systems. This is Stewart. He's also Ivan's graduate student, and during his section, he'll give a more detailed intro since he doesn't have the mic right now. So this first part of this presentation is going to be going over the language constructs. You guys should know most of these since you have been working on assignment 1. So I'll try and go through them quickly and leave the slides for you as a reference. And then we'll go into more detail on the concurrency language constructs. So what is Go? Like I said, it's basically a language built for systems. And so it's a C-style language that's statically typed with minimal type declarations. There's first-class functions, which I'll talk about. And then it's designed to feel like a scripting language. So you won't get burdened too much by syntax, but you still have the type declarations and ways to express systems. For documentation, there are 3 main key parts of the documentation, which is listed here. And if you looked at the slides ahead of time, you could have gone through them. And this talk is loosely mirrored to effective Go. So the Go tool, how you run it, and then how you also install it. You guys should know the run tool because I'm assuming that's what you've been using. The install tool is more important when it comes to third-party packages like GoVector or creating very complicated systems with multiple files. Same with the workspace. So your workspace should actually be in this format where you have a folder and the subfolder of bin, package, and source. That wasn't necessary for this assignment, but I would highly recommend moving to this style for later assignments when your code starts to get more complicated, and you will start using third-party packages if we require it. And so there is a link so you can look at them further. Environment, there's Go path and Go root, and there's a different way to set these in Windows, which we have a link on how to set that up if you choose a Windows laptop. But if you're Unix-based, so either a Mac or a Linux/Unix, it's just setting the environment variable using export. And again, we have links for this. So the actual language. Variable names, the key about variable names, which could trip you up later on, is going to be the capitalization. So a capitalized first letter, if the word is capitalized, it's a public variable. If it is not capitalized, it's a private variable. And this is important because when it comes to structures, like opaque in this sense, when you want to marshal those structures, it will not include the private variables. It will only include the public. So if you're going to want to send a structure over the network, which you'll be doing a lot in this class, make sure the important parts are public. So that's the one big key thing to take away from this. Yes?
And so this is by default, no having to declare public this or that, just if it's capital, Go will immediately expose.
Yes, exactly. So that's, you can see it as a simplification that's easy, but it's also very easy to write bugs, basically, because you might assume that you have to put public or private to make a variable private. But since it has to do with the capitalization, you have to pay attention to your variable names. Any other questions? Okay. Semicolons. So this Go is based in C, or is C-like. So there are semicolons, but they're inferred at the end of the line, so you don't need them. They only come into play with for loops and if statements. So instead of needing the parentheses in your for loop, it's the same as C, just without the parentheses. In your if statement, you can have multiple, basically, statements. You can create a variable, and then you can have a conditional and separate them with a semicolon. Other than that, you don't really need it. It's inferred. So for control structures, there's if, for, and switch, which behave almost exactly to the way they do in C. Switch statements break automatically, though, so you don't need a break statement. You can put it in there, but it won't do anything. Another thing to note is there are select statements, which Stewart would talk about in detail during our code example, and there is no while loop. So you will do that by basically making one of the ways to get a while loop is by making an infinite for loop. Question?
If there's no break per step, can I then change multiple, I guess, conditions in the same case if I wanted them all to go down the same path?
You wouldn't.
I can cover this.
Yeah, go ahead.
You can. The breaks are implicit. There's another language structure called fall through. So if you want to chain multiple ones together, at the bottom of the case statement, you write fall through and you'll just keep going.
So for assignment, redeclaration, and type conversion. There are var declarations where you do var a int, which creates a new variable, and then there's the colon equals operator, which will define a new variable at that given scope. So this is another way you can run into bugs, basically, is if you define var a int, and then within that this if statement, you do a colon equals b. A will only equal b inside that if statement, because the colon equals creates a variable within that scope. Since it's within the scope of the if statement, once you're outside of the if statement, it's 0 because that's what the value was before the if statement. Does that make sense to everybody? Yes? OK. So be careful where you have your colon equals and regular equals. Yes?
Depends on the version of Go, but I could have swore I ran into a bug whereby I hadn't initialized values.
Yes.
Whereas here it looks as though that's what you've done there with A at the beginning. Would that, throw up at you and cause a problem, or is this something that maybe I just done wrong?
I would have to see the error. Do you know, Stu?
Sorry, what was the question again?
I could have swore when I was writing my assignment 1 that I tried to declare a variable with the intention to initialize it later, and the compiler gave me an error from that.
Right, so that will happen if you use the colon equals, and then you don't use the variable later.
Okay.
If you just do a variable declaration, it should be okay. But typically, Go doesn't like it when you try to initialize variables and then don't use them for anything.
Right.
I don't think that's a versioning thing, though. I think that was around 6.1.0.
Yeah.
In line 4, why is B assigned 0?
Oh, that's a typo. It should be assigned 4. Yeah. So we make mistakes too. OK. To convert a variable type, you can just do the type, and then in parentheses the variable you want to convert. So in this example, I'm converting an integer to a float. But this doesn't always hold true, because how do you convert a string to an integer? To do that, you need a library called string conversion. And if you do a quick Google as to how to convert string to float or string to int, you'll find that for Golang. And you can do the same conversion with bytes to a string. Those will work with just string, parentheses, and then a byte array. Okay. Are there any questions on this? OK. And then functions and the blank identifier. So functions are first class. They can have multiple return types and be anonymous. The second return values are often error codes, and sometimes you just want to ignore those. But Go will get mad at you because you can't create a variable and then not use it. So the way to get around this is using the blank identifier, which is just an underscore. And this will be a placeholder for the unused variable, and it will get rid of it harmlessly. The neat thing about Go is that you can have multiple return types, and you can actually give a label to those return types. So in the double name example, we actually force the return types to be called number and text, whereas in just the double example, we return an int and a string. Are there questions? OK. And then the first class part of a function means that a function can actually be passed to other functions. So it's kind of like, I guess, a pointer in a sense. Yeah, it's like you can treat a function like any other variable. And we'll see that when we get to structures and data structures like that. Questions? OK. So defer is another useful thing in Go, where you can basically defer a method to only be executed at the end of its scope. So in this function, we defer a couple of prints. And the key thing to notice here is that it's not FIFO. It's LIFO. It's like a stack. So we print A, B, C, because the other functions are deferred. Then we print x, y, z. So when you defer things and the ordering matters, keep in mind that it's last in, first out. Does that make sense to everybody? Okay. So for new constructors and make, this is other ways to make variables. New will return a pointer to zeroed allocated memory. This is necessary when you're creating non-basic types. Make will returns allocated memory for arrays, maps, and channels. And if you notice in the comment here, we make it explicit that A and B are slices. That's because slices are different than arrays. And I'll get to that in the next slide. Are there any questions? Yes?
When would you use new versus make?
So make is only used on structures that the language defines by itself, like maps and channels. You use new if you're allocating like your own structure, like you made a type with a bunch of different variables in it, then you have to use new.
Yes?
What about an array of 0 types?
Well, you would initialize the array with map, and then each type you would initialize with, or each like allocation inside of that you would initialize with new.
Okay. So data structures, arrays, the key thing here is arrays are passed by value, which is different than a language like Java. Slices are a reference to a C array, so you can think of them as a wrapper, and they are going to be passed by reference. So you're going to want to keep in mind if you create an array, if you copy it or if you pass it to a function, it will copy all of the values and create a new array. So basically use slices. To create an array, you need to have the size be in the declaration. So C in this first code example is an array. If I took out that 5 parameter, it would be a slice. So that's important to keep in mind. Another way to create a slice is to actually get sections of arrays, and you can do that with the colon inside the brackets, as you can see in D. So I'm creating a slice of the first 3 elements, 0, 1, and 2. And then you can create a map and actually instantiate it in the same line, as you can see with M. And then the append function, this is important to remember, is it will return the result. It does not actually append the the slice or the array, and then you can just move on. You have to do slice or array equals append. So if I didn't have that D equals, the append would have been, lost. It would have been the original slice. Does that make sense? Yes?
So slicers are immutable and arrays are immutable, or is that kind of what it is, or not really?
Well, so the difference between slices and arrays is that a slice is the reference to the array. It's like a wrapper. It's the Go wrapper around an array. They made an array like a primitive, in a sense, to where the array is passed by value, and it's a little bit stricter. Where append comes in, I don't know why they made append this way, because it would make more sense if the append call would just change your slice, and that was it. You didn't have to reassign it. But I just wanted to point out that when you call append, you have to reassign it. So you don't make that mistake in your code thinking you're appending values, but you're not. Does that answer your question? Probably not. More or less. Okay. Yes.
So how does that relate to the previous slide where A and B are slices?
Right. So A and B are slices because I did not give it a size. So the way you differentiate creating a slice in an array is if you give it a size within the bracket parameter. And can you use new and make with arrays?
Yeah, no, the arrays you actually have to allocate directly. Where when you're using new and make, you're automatically getting a slice. So
Okay.
this is a little tricky, so I'll take 1 second to write this out on the board. Okay, so when you write something like make, and we're going to do an array of integers, and we'll say it's size 3. And we'll make A equal to that. So what we've done here is actually 2 things. We've created an array, that's hidden. What we get back is actually a slice that points to it. So in memory, you've got an array like this, like slot 1, slot 2, slot 3, and what you get back is a pointer to that, and that's what A is equal to. Is this big enough for everyone? Can they see that? Yeah.
Does this make sense now? Yes? Okay. So structures, they're like C structs but more powerful. And what I mean by more powerful is you can actually have a function be a field in your structure. And yeah, so the key thing here to see is that when if you were to create an object, like in Java, you would create a separate object and have a whole bunch of methods for it, or in C, you would have to have the method headers. In Go, you can create objects within your code just by doing the parentheses, a name, and then the object, as you can see in what's this? In this line. This is creating a method for my structure, which I guess to me, because I come from a Java background, looks like an object. Does that make sense? So that's how you would kind of create your own data fields and then methods attached to those data fields. The interesting thing here is that I do have a function field. And so I set that to my dummy function right here. And so I was trying to show the two different ways you can have functions. One is as a field of your structure, and the other is the other one is more the traditional sense of having a method attached to an object. So my object calls a method. Does that make sense? Yes?
For the second function, you have self mystruct.
Yes.
Do you always have to put self?
No, that's whatever name you want to call it. It's just a variable name.
Do you have to use the variable or no?
I'm not sure.
Nope.
Nope, it doesn't throw the uninitial or unused? Okay. You don't have to. Yeah. There was another question. Yes?
So that's just saying like what kind of object it belongs to, right? It's
Yes.
So like declaring a new method for that object.
Yes.
Okay.
Right? Okay. So Stewart's kind of a Go guru. So I will be referring to him throughout this presentation. Any other questions? Okay. So interfaces, again, are different. You don't explicitly attach a structure to an interface. But they do still specify the specific behavior, and they're defined as a set of method signatures. So in order to make a structure implement an interface, it just has to implement the methods of that interface. Based off of that, what do you think? Why do you think the line right here will cause an error without running it? Oh, this one. Why does S equal R cause an error in this code? Yeah.
Because rectangle doesn't implement area.
Exactly. So the key thing to take away from here is that because rectangle doesn't implement area, it does not actually implement the interface shape. And so if you implement the methods, you automatically implement the interface. So I could have created a structure called dog and had the dog implement a method called area. Then technically it would be of the type interface shape. So that's one thing to know. So you don't really have control whether or not you implement an interface, except whether or not you implement the methods of that interface. Does that make sense to everybody? Okay. So the fun part, concurrency. In Go, you don't actually have threads. You have Goroutines, which are lightweight threads, and they're multiplexed onto the operating system threads. So they will execute concurrently in the same address space, and basically I treat them as if they were threads. There are two different ways you can create Goroutines. One is by actually calling Go and then a method, and then another one is by creating a function by doing function, parentheses, brackets, put your code inside of that, and then do the same thing, call Go function. So there's two different ways. One's not necessarily better than the other. It's just whichever one makes the most sense to you. Okay, yes?
The second one, R, when you have go func like that,
Yeah.
is that like a immediately invoke function? Or is that
When,
called immediately in that second one?
yeah, so when I, you have any?
Yeah, so it's just treated like any other thread, so it's scheduled by the operating system at that point. So if you ran multiple Go routines, they'll just be interleaved.
Okay.
So it might run initially, or potentially it would just finish running in bar and exit.
Okay.
And you will see better examples of Goroutines in Stewart's code, because it was kind of hard to get a really fleshed out example of a good Goroutine in one slide. So, any questions on Goroutines? Yes?
So the second function, what you use to invoke it?
What do you mean by invoke it?
Using the third function, you guys call.
Oh, yeah. And the third function I call bar right here. And so that's going to go up here and then hit the Goroutine and create a Goroutine and then go through the code.
But for the second one, you supply the function. What you use to call this function.
Right here?
Like round brackets after the closing code brackets.
10 and the 2 are inside the round brackets. That would make it invoke.
I guess I'm not understanding your question. So.
I think what he's asking is in the inside of bar you use go, but there's no brackets after that function definition to say that you're calling it. I think that's what he's asking about.
No brackets after the function.
Like is it?
Like you're not invoking that internal closure, I think is what he's saying.
Yeah, so if you just write the word go in front of that, that's an anonymous function, and it just goes right away.
So it runs even though you haven't put the brackets to say you're calling it?
Yep.
Okay.
Okay.
I think, is that what you were asking?
Yeah, did that answer your question? Yes? Okay. Are there any other questions from that? Because this is important to understand, especially with distributed systems.
Wait, I'm still confused about what the question was.
Okay, I think maybe there's confusion because I didn't explain very well what an anonymized function is. You sure? Okay. Stewart says we're doing this after class because his part of the tutorial is actually really helpful, and I don't want to squeeze out his part. So if you're still confused about it, I'll be here after class. Okay?
Thank you.
Yes. Okay. Channels. This is how two Goroutines or multiple Goroutines can communicate. And so they're FIFO, first in, first out, and they share data, and they can help you coordinate between your Goroutines. Basically, if you're reading from a channel, it will block if there's nothing to read. If you're writing to a channel, it will block if it's full, kind of like a producer-consumer problem. It will, let's see, and there's two types of channels. There's buffered and unbuffered. Buffered basically means you give it a size. Unbuffered, there's no size. And so to send to a channel, you just do channel and what you want to send to it. And this is to receive from a channel. And in Stewart's example, he'll go over a lot more of how channels work. But for now, I'll write up just a quick little thing as to how they work. So this will be your channel. And let's say I created a channel with basically a buffered channel of 4. And then I'm going to have a Goroutine right here that's connected to my channel, and then another Goroutine right here. So this is Goroutine 2, Goroutine 1, and then my channel. So if Goroutine 1 sends 10 into my channel, it's going to go in this slot right here. Goroutine 2 will read from the channel and then print what it read, which will be 10. And then this goes away. Does that make sense so far to everybody? Is this completely making sense? Should I continue? Or do you want me to move on? Yeah.
If they're in separate functions, when they are passing through like the channel, do they have references to their variable names? Or do you have to like pass this?
So you're not passing like the variable, you're passing the value of the variable.
Okay.
Does that make sense?
You can assign it in any way. Like say for example, there's like a second thing in that channel.
A second what?
A second value that's in the channel.
Yeah. So if I have 10 and then 5.
Yeah, so like you would need the name of the variable that's pointing to that in order to access it in the second Goroutines.
Oh, I think what you're saying is Goroutine 2 needs to have access to this C variable.
Yeah.
Yes.
Okay.
So you will pass channels into functions, and you can see in Stewart's code later how to do that, and that will kind of show you how to link two Goroutines with the channel. So right now I'm assuming that these Goroutines both have the channel C.
Okay.
Does that make sense?
Yeah.
Okay.
Yeah. So when a channel's blocking because it can't read because there's nothing there yet, would that implicitly yield like the thread so that it can be used by other stuff, or are you literally blocking that? Like how is there an implicit yield there? I guess.
Yeah, the thread just blocks. If you're waiting on a channel with nothing in it, it'll just sit there.
So the thread will be idle and it won't be able to do other work, kind of thing. So is there a way to? Is there a construct for like yield in that situation?
We'll talk about that.
Okay.
I think that, yeah.
Is this an example of a buffer channel?
Yes, this is buffered.
What about like for unbuffered case, if you're getting way too much data that you can possibly consume, what would happen?
Then the sender won't block because the buffer's never full until you're out of memory, I would guess. Right, Stu?
Yeah, so
Okay.
if the channel is full because the producer is producing too much, then the producer will block once the channel's full. So it won't be able to write it.
But in the unbuffered case where the channel technically doesn't have a size, I think that's what you're asking about, right?
Yeah, so it just runs out of your memory.
Or will it still block?
It'll still block.
It'll still block. Okay, there we go. So it'll still block even in the unbuffered case. Yeah. It will just block once you have no more space. It won't block on a predefined number because it's unbuffered. Does that make sense?
When will it block though? That's what, maybe I'll just Google it.
We can talk after class about that as well, because we're going to have a little bit more content to get through.
Was there another question? Oh, yeah.
What if both Goroutines sends a 10? What does the channel look like?
If they both send a 10.
There would be two 10s in the channel.
So is this bidirectional? Like, can Goroutine 1?
We'll talk about that.
Yeah. So Stewart has a really awesome code example. That's why he's trying to push us along, which shows a lot more capabilities than what I'm showing.
Or like
Is everyone good so far? So do you understand the blocking when it is buffered, or do I need to go over that? Okay, so last thing, errors. There is a type called error, which allows you to add detailed error information, and you can implement your own custom errors using that interface. So the error interface has one method, and it's error with a capital E. So all you have to do to implement that is create your structure with a method called error capital E. And so this is useful as you get into more complicated programming. If you refuse to use logging, you can construct your own error messages to give you more details as to where in your code the error happened, what method, circumstances around it, and stuff like that. Here's our helpful links and resources slide. Please go over it. If the concurrency, well, if you want to see a cool way to visualize Goroutines and channels, there's a blog post and a video where someone put together a visualization tool. It's a little bit hard to see, so if you're still confused about Goroutines and channels, try and talk it over with us first so those visualizations don't confuse you. Does that make sense? Okay. Here's our second question.
Testing. Is this good? Can everyone hear me? A little low? A little low? How about now? No? Better? I might just shout. I'll do this. Okay, so question 2. I'll introduce myself first. Hi, my name's Stewart. I'm one of Ivan's graduate students. I pretty much do distributed systems and Go full-time for like 2 years now. So use me as a resource, because a lot of this, like your code, I'll just be able to sight read it. My office hours are Monday in X339 from 2 to 3. Okay, so why are specifications extra important for distributed systems?
There's a bunch of extra crap that can go wrong.
Right. They're hard. So if you've got a specification, it's a concise, simple format that's a lot easier to get right than actually writing the code. So we're going to talk a little bit about specifications and how you can use them, and the sort of mental models that you can construct to like guide yourself through developing a system. So I've built a sample system for you guys. And the metaphor we're going to be going with is the idea of a game of catch. So before we get into the actual like spec, just imagine that you're standing around with a group of people and you're throwing a ball around. There's a probability that you catch it and a probability that you drop it. Okay, so Ivan is going to give you something that looks a little bit like this. Some very concise English language that says exactly how the system's supposed to behave. So in this game, there are 3 nodes, A, B, and C, playing a game of catch. The node either has the ball, is open for a catch, or is not ready. One node has the ball, the others don't. The node with the ball will wait for a node to say, give it to me, I'm open, or it'll become impatient and throw it to a random node in the system. If a node that is not ready gets the ball passed to it, it's just going to drop it and the game ends. So you're going to get something like this, and now this is an English specification, but there's a better way to reason about this. And that is a finite state machine. These are super useful, because as you can see, this is a lot more concise than the English specification. And sometimes pictorial stuff is just useful as well, because you can just see it all at once. So this is the exact same thing. Starting in the has ball state, it's going to these aren't nodes, by the way. These are like state. It'll time out and throw it to a random node, or it'll hear I'm open, at which point it transitions to the not open state by throwing the ball. So you can think of this in a normal game. If you pitch a ball to somebody and you're like this and they bat it right back, you're going to catch it in the teeth. So it takes some time, and eventually it'll yell, I'm open, I'm ready for the ball. And if it then gets it, it catches it and goes back to the initial state. Is everyone pretty clear on this? Questions? Let's go through a simple example. Okay, so this is a timeline. These are actually nodes right now, and the state is encoded by a color on the timeline. So initially, N0 starts with the ball, and N1 and N2 are both in the not ready state. N1 times out, and it says, hey, I'm ready now. And it broadcasts that I'm ready message to the other 2 nodes in the system. And then it receives a pass back from N0. N2 doesn't do anything because it doesn't have the ball. That wasn't part of the spec, so it just ignores the message. N1 then is in the has ball state, and eventually times out and throws it to N2. N2 wasn't ready, it drops it, and the game is over. Does that make sense? I'm going to let this percolate for a second. I'll ask you guys a question. What happens if the I'm open message fails? That first one that N1 sends out to N0.
N0 timeout.
Right, okay, cool. Just use that as a benchmark. Okay, so we've got our specification lined up. We know how the system's supposed to behave. And now we're going to actually start thinking about how we're going to implement this thing. So there's really 3 components to the sort of systems you guys are going to be building, and a lot of it just has to do with like the size. Obviously, if you're developing for like industry, there's going to be other concerns, like the amount of people working on it, and you're going to have different constraints. But for this, there's 3 steps. There's bootstrapping. Oh, you guys have also probably already seen all of this working even on A1. Bootstrapping is like getting your system ready, initializing all of your variables. Then part 2 is deciding how your concurrency scheme is going to work. So what threads are going to be running at the same time. And then the last thing is going to be basically our state machine, and we're going to do that in the form of a select loop. I already kind of went over this. Okay, so now we're getting right into concrete code examples. Imports. This is what it looks like. It's very nice. It's not like C where you have to write the word import in front of everything. These are particularly useful libraries that I'll be using in my code. So bytes is this sort of abstract version of a byte array that allows you to kind of read in unbounded amounts of information. So it's a little safer. I tend to use it when doing network reads because you're never going to run into the situation where you allocated a 256 size buffer and then you received a 257 size message. Encoding GOB is useful. The GOB encoding language is a self-describing data format that's specific to Go. The flag library, also very good. It's the standard for how you pass arguments to functions or to programs in Go. I'll have an example of that up. FMT is the printing. Log. Log is very useful. So some of you guys were probably debugging using println statements. Raise your hand if you were just printing stuff. That was everyone. Okay, so pay attention to this. So the log format, I'll have an example of how to initialize it. You put a little prefix in front of it, and when the actual function itself, or when it runs, it'll just be a println statement, but it'll have a prefix that says what machine it's on, or you can make it whatever you want. And then it'll also give you the line of code. This is super useful if you have lots of println statements and they're all ripping around concurrently. Math.ran's not important. Net's going to be everywhere. OS. The little thing at the end there is just a convenience thing. You can see time. I've put the letter T out in front of it. That's an abbreviation. So rather than writing time dot after or something, which is a library function, you can just write T dot after. I don't recommend doing this a lot because it limits the number of variables that you can have the name T. But yeah, it's convenient. Global variables. Okay, you've probably heard global variables are bad, but sometimes they're really darn convenient. So in my system, I have made some global variables. Things that you should really think about what you make global, because it's the things that all the threads are going to be able to touch. So if I recommend having things that you're only going to be read-only. So the first things are just the connection, the port, a hard-coded list of who's going to be in the cluster, the logger, an array of addresses that we're going to send and receive from. And then we get into the state variables, which are the ones that are the most important because they get touched by everything. So ball is if you have the ball, open is if you're open, and catches is the number of catches that have been made in the system so far. And that's kind of the interesting one because it's you need distributed agreement to find out how many catches there are. Okay, so there's really only 2 bits of information in the spec, so it's about as simple as I could make it. Okay, bootstrapping. An init function. It's pretty straightforward. This is the logger format I was talking about. So this will have the prefix initializing, and it'll just go to standard out. Then there's functions set flags, check args, set up your peers, and get a connection, at which point you'll be done, and you can change the prefix to go and be the IP port so that you know that you're done initializing and your system's running. And let's look at those in particular. So this is the format for parsing arguments. I'm not going to go through this completely because there's quite a bit of text here. Just when you use the example that I've given you, so when you actually parse arguments in the future, just copy and paste. One thing I'm doing here that is particularly important is making sure that the IP port passed in is actually part of the cluster because we denoted ahead of time who was in the cluster. So that's the sort of thing that you want to check is correct. And also, I'm a personal fan of just killing things that aren't initialized correctly. So we've got if not found logger.fatalf. It's another convenience thing about the loggers is that you can write panics, you can write errors, and you can write fatals directly from them. Resolving addresses. This is more things that you can just copy and paste out of the text because it's pretty basic and there's not a lot of thinking behind it. So set up peers. The key thing about this, I'm just iterating through that list of strings like the localhost 19,000. Key to this is that I'm not adding myself to the peer list. You will find that you end up in really, really strange scenarios if you're sending yourself messages. So I recommend doing that in all cases. And this getAddr function is pretty static. I wrote that 2 years ago and I'm still using it. And this is also pretty basic, just UDP connection. You have to resolve the address and you have to listen on it, and then you'll just get a connection back. What's particularly important here is the string argument that I'm passing to both of them. So it's just text, UDP. So there's like a pretty big space of arguments that you could pass there. The list is in the net library. There's a description of it. You can pass like UDP4, UDP6, TCP, TCP4, TCP6, and that's just the like networking that you're going to use. Okay, so this is a pretty tricky slide, so we'll take some time with it and think about questions to ask. Okay, we're going to have, oh, did I skip something? I did skip something. Okay, so that's bootstrapping. Are there any questions about bootstrapping? Yeah?
What are the differences between listen UDP and using a read function?
So listen UDP is just getting a connection. So you will, once you get that connection out, you'll listen on that, or you'll read from that, or write to it. Okay, so we're into part 2 now, which is defining your asynchronous structures. I've put it into 3. There's a reading routine. There's a main select loop where our logic is going to be, and there's a writing routine. Partitioning your system like this can be particularly beneficial to you as far as organization goes. Because if in your select loop you're also doing reading, it's going to get big, and it's going to be a hassle to look at it all. So I'm going to define these separate methods, run them, and give them the communication capabilities so that they can all talk to one another. Another thing to note, this is what's known as the event model. So everything here is serialized. Things are coming in on the read, they're being passed through a channel, the select loop handles it, and then it goes out on the write. And that has to happen like all in one go. New things coming in on the read will just wait until a write's been made, or until a timer's been fired or something like that. Alternative to this would be if you started a new thread every time you received a message. So this is kind of classic in like how you would serve a web page, where you would just wait for the message to come in and start a new thread to issue like requests to a client. When you're writing distributed systems, if there's shared state, in this case, like there's those 2 bits, the ball and whether they're open or not, you can imagine that if you started new threads for each one, they could contest each other and how they manipulated those variables, and you could end up with like race conditions. So I think this is particularly useful, although I was told on Wednesday by Andrew Warfield that this was way more complicated than the multi-threaded version, but I'll take his word for it. Okay, so this is the init function first, and then I established some channels. So one of the fun things in Go is that you can do multiple declarations on the same line, and you can see that here. We're defining read message and write message, which are channels of size 1, and type message, which means that you're only handling one at a time, they're unbuffered, and they're passing a message structure, which I'll define in a slide or 2. And then I'm immediately launching them. I'm passing them the connection that I established within it, and it's a global variable, so I can just pass it in. And the moment that those routines are running, your system's up and going. It can start communicating, even though we're not in the main loop yet. The next one I was told was also kind of tricky to understand, and it gets back to your question about directions of channels. So the first channels, read and write, are directionless, which means they can go in either direction. Now, realistically, the write you only really want to spit to it, and you only want to receive from the message. So you could type them. And an example of this is in the timers, because the timer library only has read from channels. So if you look where it says make and then there's a pointer, that means that you can only read from that. So these are timers that are going to make transitions from like that random, like I'm bored now or I'm open now. And then, yeah, so the big line with T dot after, I'm just setting up the timeouts. Common knowledge is like sort of a weird thing. It's well defined in distributed system literature, so I'm not going to go totally into it. But the idea is that there's some things that are kind of essential in the bootstrapping mechanism that every node in the system will know. So in this, everyone knows that if you have IP port localhost 19,000, it starts with the ball. We've set it up so that ball is equal true. That's initializing. And common knowledge is sort of this iterative thing where everyone could say, I know that localhost 19,000 started with the ball, but I also know that everyone else knew that it started with the ball. I know that everyone else knew that everyone else knew that everyone else knew that someone started with the ball. Anyways, yeah, so when you bootstrap stuff like this, it's important to know what sort of information you're dealing with. Okay, the message structure. Oh, we got 5 minutes left. Okay, so a convenient way to make a bunch of messages is to have some sort of constant with this IOTA just iterates, so pass is 1, open is 2. The message structure itself, I'm just putting the catches and the type inside of it. I've also, for convenience, put the address of the person who was sending it. Notice that it's a lowercase a, so it's not actually being sent over the network. That's something I'm going to be adding in when I receive messages. Next. Listen routine. This is a long one. This is just a big for loop. All it does is it receives into a buffer, and then it decodes into this message structure. That's the gob decode and network, which is the, it's just attached to this bytes buffer. And then we are transferring from the bytes buffer in network.write, and then we're decoding. So we have to go through this kind of quick, but that's what's going on there. Notice at the very end, the read message is actually being sent on the channel that was passed in. So it's just this continuous loop, just chugging along, receiving messages from the network and passing it into the program using a channel. Quick question. I'm a bad programmer. What did I do wrong here that would be bad? Can anyone tell? You get a bonus point if you can tell.
Well, I was going to say that there's no return value, but you didn't declare one, so that shouldn't be an issue.
Yeah, so the return value is kind of like the channel, because it's just a communication thing. So what I've done here is at the very beginning, or inside this for loop, I'm redeclaring message and network every single time the for loop goes. And you can imagine if this was C, that would start to get large eventually, as well as this bytes buffer. So every time this thing loops, I'm declaring a new variable with like 1,000 bytes of size. This doesn't matter in Go because it has garbage collection. Keep that in mind. The same thing, the writing routine is just the exact inverse. It waits on a channel, receives a message, writes it out on the wire. I made the same mistake here. Okay, the event loop. This is where things get hairy, and this is where like the key intuitions need to play in, because this is where we're going to like put all of our logic. This is how I recommend you start. Build a skeleton. Just like handle async stuff. So this right here is just like, if you hook your system up at this point, it will still receive messages and like logically go to the correct place. You're just setting up your control flow here. This is convenient because it sits on your screen like all at once. This is like a kid who's just going to sit there and like let the ball hit them in the face. Like it'll actually, it will still operate semi-correctly, but we're missing any manipulation of the state variables. So let's add that in. Okay. This is pretty much it. I mean, we're doing the manipulation when open is called, the ball is true. Or if you're open and you receive an open message and you have the ball, you say okay and you pass it back to the person who asked for it. If you receive a pass and you're open, now you have the ball. In the case where the open timer fires, open becomes true. And in the case where the pass timer fails, you lose the ball and you throw it to someone random. Now, we've seen this before. You guys remember where we saw this? Not too long ago. It's our trusty old friend, the spec. It's pretty much all there. And this is one of the reasons Go is pretty popular, is because you can do things like have a specification that looks like this in this like abstract form and represent it concisely. Right here. This sits on your screen all at once. Like you can look at this whole thing right now. It's a distributed system. But all the logic is in one place. So if you look at a lot of big systems, they'll always have these gigantic select loops that look like this with tons of logic inside. It's not done, though. We still need to actually send messages. Yep?
What exactly does select itself do?
Oh, yeah, sorry. Okay, so select loop is a lot like a switch statement, except instead of having conditions, you have channels. So what this is doing is if the read message gets fired, that first case is what's going to get executed. So you just you define all these channels that are all concurrent, and now we've created this big select loop, which will listen to all of them at the same time. So when you guys were asking earlier about like, what do you do if you've got a channel that you're waiting on and there's nothing there? Well, put it in a select loop, have a second channel with a timer on it, and make a timeout so that you could exit if you wanted to.
And each iteration of this loop only reads from one channel and then continues on.
Correct.
Okay.
So it'll fire, it'll go into its segment, and then it'll go back up into like the select wait. Yeah, that's key.
But what would happen if you had two channels both coming through and like, not a race condition specifically, but the second channel that hadn't been processed yet will still be queued, and then on the next...
Yep, so let's say two come in nanoseconds apart. The one that comes in first will be dealt with first. The one that comes in second will be dealt with second.
On the next iteration.
Yep.
Does select block?
Select, well, yeah, select will block until there's any one of those channels fires. Other questions? Okay, we're pretty much out of time, so I'm going to go through this last part really quick, and you can look at the code if you want to. Back to the spec. So this is just the full implementation of those states. If open, we're just taking the message and we're setting it to pass, so just set the message fields. And then the same state transition as before, ball becomes false. We are resetting the open timer and logging it, and then actually writing the message. So what's key here is that I've kind of like partitioned what's going on. There's the set up your message, perform your state transition, log whatever you need to, and then write the message. That's key. Don't try to like write the message before you've changed your state around. It'll just get messy. So like this order is key. I would recommend going back through the code and like looking at this. And I've done the exact same thing for the other ones as well. But it looks like we're out of time, guys. So have a nice weekend. It was wonderful talking with you.
Come to our office hours, or you can post them on Piazza, or I think I allowed everyone to comment on the slides as well. So we'll leave the slide sharing link that we posted on Piazza up. You can write comments, and we'll answer there as well, so you can kind of see them with the slides.
Come and talk to us now.
Oh yeah, and we'll be here for a little bit.
Wait, I made us.